Section 8.5, adding and subtracting rational expressions. All right, so here's where we get to denominators and wondering, what do we do when denominators are the same? What do we do when denominators are different for adding and subtracting? Now what's led up to this is we worked on multiplying and dividing rational expressions, and the reason for that is specifically with dividing rational expressions, if we know that we can find the factored form of rational expressions, and there happens to be like factors in the numerator and the denominator, we are able to cancel. Well, we're using that kind of a line of thinking here along the lines of that with this adding and subtracting rational expressions. I want to find least common denominators. All right. So when it's like denominators, that means we just worry about adding or subtracting the numerator portions of these rational expressions. And here we see some examples of just simple fraction work. So to add or subtract rational expressions with like denominators, simply add or subtract their numerators, then place the result over the common denominator. Here are some examples of that. So let's try a few of these, and then we'll get to the more exciting stuff, because that's when our denominators aren't the same. So here we see we have like denominators 5x and 5x, which means when I add these two together, or in this case subtract these two together, I'm going to have a 5x in the denominator. So it's simply a matter of taking the numerators and subtracting them. You get 10 over 5x. 10 over 5 reduces to a 2. And so we'll always take these rational expressions and reduce them. And so that one becomes 2 over x. Here we have another situation where denominators are the same. So I know that I'm going to have as a denominator 2x plus 5. Now in this case, the numerators are not like terms. So when I add them together, I just get 3x plus 1. And looking at the numerator and the denominator, none of those can be factored. I can't pull anything out. And so in this case, I would be simplified as far as I can get right there. So let's go and take a look at what happens when we have different denominators. So unlike denominators, now we find a common denominator. We write each expression using the common denominator, then add or subtract it. So here we have a few examples. Now it is noted that you can always find a common denominator of two rational expressions by multiplying their denominators. But that common denominator may not be the least common denominator. And really, we want to try and find the least common denominator so that we have less simplifying to do in our rational expression here. So here's some examples. Denominator C, denominator D. We find out that they have a common denominator of CD, and so that means the A over C has to get multiplied by D over D, and the B over D has to get multiplied by C over C, and then we get AD plus BC over CD in the denominator. All right, so let's apply that now with some of our rational expressions. First, let's talk about the whole idea of a least common multiple, which is going to help us find a least common denominator. Let's just take two numbers, 12, 18, for example, and let's find the multiples of these numbers. Let's see, multiples would be when we take this number and we multiply it by 1, and multiply it by 2, and 3, and so on. So the multiples of 12. 12 times 1, 12 times 2, 12 times 3, 12 times 4, and so on. Multiples of 18. 18 times 1, 18 times 2, 18 times 3, 18 times 4, and again, so on. So when you're looking for the least common multiple, if this was a denominator, then I would look and find the number that they have in common, the smallest number that they have in common, and I would see, in this case, that the least common multiple is a 36. So we're going to do that now with rational expressions. How can we come up with the least common multiples of a 30 of a rational expression with another one? Well, it has to do with the factoring. And if I can factor these rational expressions and then find what common factors they have, and then find out what's missing to make them look the same, then that will be how I come up with my least common multiple. So back over on the number example, let me show you what that would look like if we did this in factor form. So back to 12. The factors of 12, if I'm talking about prime here, I can have 2 times 2 times 3. Those are the prime factorization of 12. And then 18 would be 2 times 3 times 3. Those would be my prime factors for each of those numbers. So when I'm looking for the least common multiple, and it's in a factored form, I want to find out what do they have in common. So they both, 12 and 18, both have at least a factor of 2 in common. They both have a factor of 3 in common. So far, my least common multiple would be a 2 times a 3. And then I have what's different about them. So the 12 has a factor of an additional 2, and the 18 has a factor that's an additional 3. And so since those are different, if I wanted to find the least common multiple in factored form of 12 of 18, I would have to multiply by the pieces that are different, so the 2 and the 3. And then if I go 2 times 3 times 2 times 3, I get 36. And that's what we're going to do with rational expressions. Same kind of a concept. So 5x squared minus 45. Factor out of 5 is a GCF. But wait, x squared minus 9 is the difference of 2 squares. So I'm going to say x minus 3 and x plus 3. All right, let's go take a look at 4x squared plus 24x plus 36. Well, we know I can pull out a GCF of a 4, get an x squared plus a 6x plus a 9. But that factors down into a 4 and an x plus 3 quantity squared, which I'm going to write it, though, as 4 times the binomial x plus 3 and x plus 3. Okay, so now what we're looking at is we're looking at the factored forms of both of these polynomials. And like we did with our numbers over there, 12 and 18, we found out what do they have in common. And it looks as though they both have an x plus 3 in common. So that's going to be a part of my LCD, x plus 3. And then apart from that, they don't have anything else in common. There's an x minus 3 up in the top expression. There's an additional x plus 3 in the bottom expression. And the top one has a 5 and the other one has a 4. So now what I want to do is I want to make these two factored forms look the same. I want to change the 5 times x minus 3, x plus 3. I want to multiply it by some things that are missing to find a common denominator, a common multiple. I'm going to do the same thing with the red, 4 times x plus 3 and x plus 3. So we know at least their LCD has to have an x plus 3 in there. And then now I've just got all these extra parts, right? And just like we did with the numbers, the parts that were different, they multiplied with the parts that were in common, and that's how we formed our LCD. And so in this case, the parts that are different so far, I've got a 5 and a 4. So that's going to give me a 20 right there. So we have, for our LCD, so far we had that there was an x plus a 3 in common. And then now we have a 5 and a 4, because they're different. And then we've got this x minus 3, which is a part of the black expression, and that's not in common, so I have an x minus 3. That's different. But then what about this additional x plus 3? Well, I need to include that because it's different between both of my expressions here. And so really I've got that additional x plus 3 in the red that's not up in the black, and so I have an additional x plus 3 that I need to account for in the LCD. All right, so if I put this all together then, I would get 20 x plus 3, there are two of them, squared, times x minus 3. And this would be the LCD of 5x squared minus 45 and 4x squared plus 24x plus 36. Yes, I could go ahead and take x plus 3 squared and FOIL it out, get x squared plus 6x plus 9, and then take that, multiply it by x minus 3, and then take that, multiply it by 20. We're going to just leave it in factored form here. So there is your LCD of those two rational expressions. Another way to maybe look at that, we'll do it here with the second example, is to, again, we talked about figuring out, we want to make them look the same, so what do I need to multiply each of them by to make them become the same value or same expression? And we'll try and look at that approach here with B. All right, so we have our two expressions, 4x squared and 4x squared. Factor-wise, we can't do anything with that, so we leave that one alone. And then we have the 8x squared minus 12x. Well, we can pull out of that a 4x, and I'll be left with a 2x minus a 3. Okay, so here's the other way to look at common multiples. I have 4x squared, and I have a 4x times a 2x minus 3. I want them to be the same thing. I want them to include the same parts. So, for example, the 4x squared, it's obviously missing some of the parts from 4x times 2x minus 3. One of the things it's missing from the 4x times 2x minus 3 is it's missing 2x minus 3. It already accounts for the 4, and it actually already accounts for this x here because this is an x squared. So multiplying those two things together, 4x squared times 2x minus 3, would create my common multiple for that rational expression. Let's do the same thing for the red one now. So we started with 2x minus 3 times 4x. And now we go find out what is it missing. And we see that the only thing that this thing is missing from the 4x squared rational expression is that x squared term. So we would have to then multiply by an additional x, and then we create the 4x squared component, and then now we have 2x minus 3. So now we look at these two things. We have 4x squared, 2x minus 3, and it looks the same thing as if we were to do 4x times x, or 4x squared times 2x minus 3, and so this then is my LCD. 4x squared times 2x minus 3. Just find the pieces that are different about them. Make the two expressions look the same by multiplying the individual expressions by those missing parts. So there's our LCD for that one. All right, let's go ahead and put this in action now. Let's do some adding and subtracting. So unlike denominators here, so we want to find LCDs. We need to come up with the LCD for 10x squared and 5x squared minus 10x. All right. So I'm going to go ahead and put 10x squared in here, and I'm going to go ahead and put 5x squared minus 10x, and we're going to factor these. So this is going to become 5x times x minus 2. 10x squared, I can't really factor anything, so it's pretty much ready to rock and roll there. Now I'm looking for, well, what do they have in common? They really don't have anything in common. One of them has a 10, one of them has a 5, one of them has an x squared, one of them has an x, one has an x minus 2, and the other one does not. So here, I'm going to go ahead and do the approach of let's make them look the same. If I kind of separate them, like if I compare maybe just the coefficient parts, the 10 and the 5. Well, if I looked at the least common multiple of a 10 and a 5, I would be at a 10. So we know 10 is going to be a part of my least common multiple. Then what if I look at just the x variable parts? X cubed, or x squared, and x. If I looked at those, I'd say the least common multiple would be an x squared. By the way, when you have variables or binomials that are being raised to a power, you always take the highest power. That's going to be your least common multiple. So, for example, an x squared and an x, factor-wise, this is an x times an x, this is just an x. So here's what they have in common, and then there's a different about them. So x squared would be my least common multiple. Just take the highest power. And then we've got individual x minus 2, which is just its own thing. That's unique. And so, in terms of the LCD for this, we would say the 10 and the 5 would become a 10. The x squared and the x would become an x squared. And then the x minus 2 is its own piece. So I'd have 10x squared times x minus 2. If I'm going to do the, hey, let's find what's missing thing, we start out with a 10x squared, and we realize that that rational expression is missing the x minus 2 off of the other one. And if we start out with the 5x and the x minus 2 here, we realize that it is missing a 2 to make the 10 and an x to make the x squared. Now, the reason I'm looking at it this way, where I've separated it and found out what the missing parts are, for each of the expressions, because the missing parts are now what I multiply the numerator and the denominator by for each of the original expressions to come up with my added polynomial here. So I mean this. If my original was a 3 over a 10x squared, and we said the missing part on that polynomial was that the denominator is missing the x minus 2, and that means I'm going to multiply the top and the bottom by this x minus 2 value here. And then we add to the original 2x over, and I'm going to write it in packet form, 5x times x minus 2 rational expression. What's missing on the denominator of that one, we said, was a 2 and an x. So that's what I multiply the top and the bottom by, is a 2 and an x, the missing pieces. Right? Missing piece multiplied, missing piece multiplied. And now finally we get our common denominator. So this whole thing would have a common denominator of our 10x squared times x minus 2. And on the top you have a 3x minus 6 after I distribute the 3. And then on the right hand side I have a plus 4x squared after I multiply 2x times 2x. And then I would put that in descending degree order. 4x squared plus 3x minus 6 all over 10x squared times x minus 2. And yes, you can, if you want, go ahead and distribute that and get 4x squared plus 3x minus 6 all over 10x cubed minus 20x squared. So now they're both in expanded form versus one piece being in factored form and the other one being in expanded form. So either of those will work. That's my simplified expression there. Let's try with this part B here, and we'll get into another one. Okay, LCD, let's see, we have a 4x squared, and we have a 2x times an x plus a 2. And the parts that they have in common, nothing. So I want to make them look the same. So the 4x squared would have to get multiplied by an x plus a 2 to look the same. And the 2x and x plus 2 would have to get multiplied by a 2 to make a 4 and an additional x to make a x squared. So my LCD would then be 4x squared and x plus 2. So I come over to the original problem, and I multiply by the part of the LCD that is missing. And in this case, I'm missing an x plus a 2 for this one. And then do the second expression. Again, I will show it in factor form. And that denominator is missing the additional 2x. The reason we're multiplying the same thing top and bottom is because this thing just equals 1, and I'm not changing the value of the product, just changing the way that it looks. All right, we go ahead and we distribute. Distribute 5, and then distribute 2x, and we get 5x plus 10 plus 2x squared plus 2x all over my LCD of 4x squared and x plus 2. And then we can go further with this, descending degree order, plus 7x plus 10 all over 4x squared and x plus 2. Now we are going to want to sometimes, it might be a good idea to check the numerator, because if it's a trinomial, it's possible that it can factor, so 2x squared plus 7x plus 10. In that case, I can't factor that one. But sometimes they will factor, and in doing so, they may end up canceling after it's in factored form. Maybe one of the denominator factors will be the same as one of those numerator factors, and you can cancel them. All right, last problem here. Looks a little interesting. Again, we want to factor everything first, so it's easier for us to find our multiples. So this is an x plus a 3 squared, or I'll write it as an x plus a 3, x plus a 3. And then this is the difference of 2 squared, so I can write it like so. So LCD. What do they have in common? They both have at least an x plus a 3, so that's going to be in common. What do they have that's different? Well, one of them has an x minus a 3, and the other one has another x plus 3. So my LCD will then become x plus 3 squared times x minus 3. We start out with the original over the original in factored form, and realize that in this particular polynomial, or this rational expression, the x minus 3 binomial is missing. And for the other one, the x minus 3, x plus 3, it is missing the additional x plus 3 binomial. And now I've got my like denominator, and I do my distribution, right? Foiling 2 binomials up there on the top, I get x squared minus 2x minus 3. Distributing the 6 gives me the 6x plus an 18. And all of this is over x plus 3 quantity squared times x minus 3. And that'll simplify to an x squared plus a 4x plus a 15 over x plus 3 squared x minus 3. And again, x squared plus 4x plus 15, can't factor that, so I'm not going to be able to reduce anything, and I'm done right there. Let's take a look at subtraction. Subtraction is not any different. The only thing I have to be careful with subtraction, and I would recommend doing this, is every time I'm subtracting a rational expression, maybe put brackets or a parenthesis around it to remind yourself that that negative outside has to distribute to the numerator, not the denominator and the numerator, but just to the numerator. We're going to leave the denominator alone. So the negative is going to distribute and change some values up there. All right, so LCD. Let's try the LCD on this one. We have factoring it, we get a 3 times an x minus 5 for the first denominator. Factoring this, we get an x minus 5 and an x plus a 1. So they have an x minus 5 in common. And then they have a 3 and an x plus 1. That's different. So there's your LCD. We set up 3 times x minus 5. And we discover it's missing the x plus 1 binomial. And then we subtract, and I'm going to put brackets here, 2x plus 2 over x minus 5, x plus 1, and it is missing the 3. Okay. So we distribute on the top, we get an x squared plus an x. And then this 3, if I distribute it into 2x plus a 2, I'm going to leave a negative here still. I'm going to get a 6x plus a 6. And all of this is now over 3 times x minus 5 times x plus 1. And going a little further here on the top, after we distribute that negative, I get an x squared minus a 5x minus a 6 over 3 times x minus 5 and x plus 1. Now in this case, the numerator factors. And I get an x minus a 6 and an x plus a 1 over a 3 x minus 5 x plus 1. So in this case here, we've got x plus 1s on the top and bottom. They actually cancel each other out. And we finally get to our x minus 6 over 3 times x minus 5. Or I could say x minus 6 over 3x minus 15. Alrighty. Now I could have kind of taken care of that x plus 1 actually from the beginning right here. If I were to have factored out a 2, I'd have my 2 and x plus 1 there. But if you don't factor the numerator, you just work your way down, and eventually those things will start to show up, and then you can cancel them. All right, let's try this one. Again, I'm going to be careful, remind myself I'm going to distribute. So factoring the denominator here, 3x minus 3, and an x plus a 3, and an x minus a 3. LCD, what do they have in common? X minus 3. What's different? There's a 3 and another x plus a 3. All right. So this one's missing the x plus 3 minus, brackets, parentheses, whatever, x plus 4 over an x minus 3, x plus 3, and this one is missing the 3. All right, I'll put a bracket there so we don't get them confused. Distributing 7x plus 21 minus, and again, I'll distribute first and distribute the negative afterwards, 3x plus 12 all over 3 times x minus 3x plus 3. And we'll go and distribute that negative and get 7x plus 21 minus 3x minus 12. Then we'll go a little further because we can combine like terms and get a 4x plus a 9 plus a 3 and an x minus a 3. Okay, 4x plus 9, nothing to pull out there, and so we're done. All right, you thought that was exciting. Wait till you get to this. Complex fractions. So complex fractions is a fraction that contains a fraction in its numerator or denominator, and they can be simplified with either of the two methods below. Method number 1, if necessary, simplify the numerator and denominator by writing each as a single fraction, then divide the numerator by the denominator. And in that case, we know this to be our situation where we save it, change it to multiplication, and flip the second rational expression over. Save it, change it, flip it. That's method 1. Method 2, multiply the numerator and the denominator by the least common denominator of every fraction in the numerator and denominator, then simplify. So now this is looking at the whole in its entirety, the complex fraction, versus method 1 where you're looking at simply numerator denominators and denominator denominators. All right, let's try both methods on this one then. Here we'll try method 1 on this where we're working solely with numerators. So I'm going to work up here and find an LCD, and then we're going to work here and find an LCD as well. All right, down at the bottom. The LCD of an x and an x minus a 5. There's nothing in common. Now this is a little tricky. X and x minus 5. This x and this x. Yeah, they're the same variable, but we're talking about common factors. So this is a binomial, which actually means that that x and that x are not factors. This x is its own piece. That is a part of a binomial. So I cannot say that the x is in common. The factors of x times x minus 5 are the only thing that I can put together here. They are two different pieces, so therefore they become the denominator. And it's the same situation for the LCD in the numerator. It also has an x and an x minus a 5. Now this is just coincidental. It doesn't always work out this way where they're the same thing. Okay, so we go and we work the numerator. All right, we have 6 over x minus 5, and we multiply by the missing part of the denominator, which is an x. And then we have a 1 over an x. We multiply it by the missing part of our denominator, which is an x minus a 5. So then I get a 6x plus an x minus a 5 all over x times x minus 5. And that 6x plus x minus 5 becomes 7x minus 5. Okay, there's the numerator. Let's do the denominator. Same thing. We have a 3 over x, and what's missing is the x minus 5 part. And I'm subtracting a 2 over an x minus a 5, and what's missing here is the x part of the denominator. So this is going to become 3x minus 15 minus 2x all over x times x minus 5. And 3x minus 15 minus 2x just becomes x minus 15. All right, so you've got 7x minus 5 over x times x minus 5 divided by x minus 15 over x minus 5. So now we're going to save this one, change this to multiplication, and flip this one over. And now it'll look like this. 7x minus 5 over x times x minus 5. Multiplied by the reciprocal, so x minus 5 over x minus 15. And then what happens? The denominators and the numerator factor parts are the same, and I end up with just 7x minus 5 over x minus 15, and that would be my simplified solution for that complex fraction. And again, that's using method 1 where you look at numerator LCD and denominator LCD. Now we're going to try it with the other method. This is now method 2. And the method 2 allows us to look at the LCD of every denominator. So this is LCD of all denominators, both in the numerator and in the denominator part of the complex fraction. So it means I'm looking at x plus 1, 3x, and x plus 1. So I'm using all of those, and in terms of looking what they have in common, again, they don't have anything in common. So I know that my LCD has to be a 3x, because that's unique. Now, 2 of them have x plus 1 in common. The third one does not. And so, because they all don't have it in common, I need to include it. That means x plus 1 would also be a part of this LCD. Now, that's the LCD of the entire complex fraction. So now what we do with that is we take the entire complex fraction and I multiply the numerator part of the complex fraction by this 3x x plus 1. I also multiply down in the denominator its numerator component times 3x times x plus 1. So I'm making sure that I'm multiplying that 3x times x plus 1 into this whole fraction, and I'm doing the same thing into this whole fraction, but on the denominator side. So what does this look like now? I've got a 2x over an x plus a 1 getting multiplied by 3x times x plus 1. And then on the denominator side, I have a 1 over 3x getting multiplied by 3x times x plus 1. And then I also have a 2 over x plus 1 that's getting multiplied by 3x times x plus 1. So I'm just distributing this into that binomial down there. All right, look what happens here. Your method 2 eliminates fraction over fraction, because what happens is x plus 1 in the numerator cancels with the x plus 1 factor of the LCD. And now up there I just simply get 6x squared. And in the denominator, 3x cancels with that 3x. And I end up with just x plus 1. And x plus 1 cancels with that x plus 1. And I end up with just plus 6x. And so this whole thing becomes 6x squared over 7x plus 1. And again, nothing can come out factor-wise, so there is the solution to that complex fraction using method 2. So you're going to pick and choose which one you want to work with. Do you want to make a single fraction in the numerator and a single fraction in the denominator like method 1 and then do save and change and flip it? Do you want to do method 2 where you find the denominator of all denominators and then multiply the numerator by that and the denominator by that, thus canceling fractions altogether in the tops and bottoms and ending up with a single fraction answer? So those are your two methods. Pick your poison and go with it. There we go.